Kia ora. One of the main things that integrals are used for is calculating areas. So we're going to look at a couple of techniques that let us use integrals to do that. We'll look at an example where we find the area between a couple of curves, and then we'll look at an example where we find the volume of a shape that's basically been rotated around some axis. So let's jump straight in. Fairly standard kind of question that you might come across is to find the area between two curves. So we've been given two curves. One is 4x plus y squared equals 12, and the other is x equals y. So a few things we've got to think about when we're doing this. We need to be aware of what way up our curves go and which one's on top of which other one is kind of the main things we need to think about. So I'm going to sketch some axes here just to try and get a sense for what this area might look like. Try that again. Here's my x-axis, and here is my y-axis. So let's see, 4x plus y squared equals 12. Now I could solve this for y equals something in terms of x, and I'll get a square root of some sort. But this one might be easier to draw as if we think of x as being a function of y. So this could be rearranged quite readily to become, let's see, x is equal to be 12 minus y squared, and then divide all that by 4. So it's going to be negative y squared divided by 4. And plus 3. Okay, so if you think of it as x as a function of y, that's going to be basically an upside down parabola that crosses the x-axis at 3. So we'll mark on 3 on here. Let's say 3 is this way, and our parabola is going to be kind of curving something like that. That's better. Okay, something like that. We can figure out where it crosses the y-axis if we feel like it. So that's curve number 1, and curve number 2 is x equals y, alternatively y equals x. So that's going to be a straight line that kind of goes through at 45 degrees, like this. And that's going to define our area for us in between those two curves. So what we're really trying to find is this area in here. Right, now we could break this up. If we did our integral with respect to x, then basically what that would mean is we'd be going through and being kind of finding the area of these pieces as we go through. And so when we move backwards and forwards along x, we'd get this one here. But that would have a different upper bound. It would be the y equals x function. And this is a bit hassly because it's going to involve trying to keep track of which function we're working on where, and we'll have square roots involved in our integral. And so this might not be the most straightforward way to do it. So if instead we integrate with respect to y, then effectively what we're doing is we're going up and down, finding the area of these little strips, and then multiplying them by dy to get that little piece of area. Then as we move that strip up and down and add those all up, we get the overall area. So you can see that the bottom, if we're going sort of, imagine you sort of rotate the picture around that way, or whichever way, we're going from the y equals x, or the x equals y curve, upwards to our other one, our x equals negative y squared over 4 plus 3. So the things that we don't yet know, we don't know where these intersection points are, so we're going to have to find those. We need to find out what these points here are, because we need to know which values of y, where we should start our y off and where we should stop. So that's going to be our first task. So task 1 is to find intersection points. This will give us what our limits of integration should be, where y should start and where it should finish. So we'll do it in the x form. So that means we'll have negative y squared over 4 plus 3 is equal to y. I'm not going to give you all the details of rearranging this, but it's relatively straightforward. Basically, we're going to multiply through by negative 4, and that will give us something like y squared plus 4y minus 12 equals 0. That's a quadratic, and as is often the case when someone gives you a video or a problem from a book, it will factorize nicely. Real life, unfortunately, doesn't work that way. You'll get something like y plus 6, y minus 2 equals 0. And so that tells me the two intersection points are when y is equal to -6 and y is equal to +2. Okay, that kind of tracks with our picture. So that value there is 2, and that value there is -6. All right, we're almost ready to go. Now, the curves only meet in those two places. It's not like they swap over halfway through. So to do our integral, we're always just going to go for the higher value minus the lower value. So it's going to be the parabola minus the straight line value. So our area will be, now we're integrating with respect to y, so y goes from -6 up to 2 of the more positive value, which is our curve. So that was, what did we say that was? X squared, negative y squared over 4 plus 3 is the x value there. Minus the value, the lower one, I would maybe do that in a different color just to remind ourselves that it's a different curve. That's going to be minus y, and that integral is with respect to y. Now it's just a matter of working this through, and eventually we'll come up with the answer. So that equals, let's see how good we are integrating today. That will be something like -y cubed over 12 plus 3y minus y squared over 2, and that's going to be evaluated between -6 and 2. All right, now very easy to make a mistake here, so let's just put in the 2's first. So we'll go for -2 cubed is 8, 8 over 12 plus 3 2's is 6, minus 2 squared is 4 divided by 2, which is -2. That's the two values. And now we'll do the -6 ones, maybe do a different color just to keep track. Minus -6 cubed sounds like 6 6 is a 36, 36 6 is a 216, so it's going to be -216. Just be really careful with our signs. Divided by 12. Let's see, plus 3 times -6 is -18. And then we'll go minus -6 squared is 36, divided by 2 is minus another 18. Okay, and we put all that together, and I'm just going to be lazy and use my calculator. I'm sure I could work out a lot of this, but I can't be bothered. So it's going to be -8 over 12, which is obviously 3/4, plus 6, minus 2, minus, open a big bracket, 216 over 12, cancelling off those two minus signs, minus another 36. And that overall gives me an area of 21 1/3. And to keep certain people happy, we'll put square units just to emphasize that we have calculated an area. Okay, that's an area problem done. So the things to watch out for in these problems, if you have a function or two functions that cross multiple times, so maybe you had curve one that's like that, and the second curve was like this, and you maybe wanted to find these two areas, then if you just did it the way we did it, you'll find that the pieces will always come, the one piece, if you just take one function minus the other one, without really thinking too hard about it, you might find, for example, that if you did the blue minus the orange, that you'd find that your first piece will come out to be positive, and your second piece will come out to be negative. So what you need to do is make sure you integrate the absolute value of the difference. And if your curves cross over within the region you're trying to find, then you're going to need to make sure you change the sign of what you're working on. Didn't really bother us with this problem because it was clearly we had one was above the other one for the whole range of our problem. Okay, anyway, moving on. So that's an area problem. We're now going to move on to looking at a volume problem, and it's what's called a volume of revolution. So quite often we can sort of sketch out an area of some sort or a region on the XY plane, and then we are asked to rotate it around some line to form a volume. So I'll hopefully be able to explain what that means, and then we'll be able to actually do the problem. So find the volume when the region between sine x and cosine x for x between 0 and pi over 4 radians is rotated around y equals -1. So first thing we've got to do is just get a sense for what this thing actually looks like. So if I just go down here, let's draw ourselves some axes. Now y equals -1 is, so I need to make sure I've got plenty of, I'll actually leave some space down below the axis here because this is going to end up going a bit negative. Here's x, here's y. Pi over 4 radians, that's 45 degrees. So that's the sine, that's basically the first time where sine and cosine meet each other. So let's just mark that on here. So just think 45 degrees is that first point where sine and cosine curves meet. So if I'm going to sketch on, let's go for sine x, we know that starts at 0, and by the time it gets to pi over 4, it's kind of hit about 0.7. Okay, so what's the sine one is going to look like this. Let's make sine blue, shall we? So it starts at 0, and it's going to be on its way up. Remember, its maximum is going to be at 90 degrees, so it's still going up at that point. And the cosine curve, well, that starts at 1, and it's on its way down. So it's going to look a bit like this. And they're going to meet at that point. So you can see that that kind of that traces out an area for us. So we can sort of shade that. And then it says we want to rotate it around y equals -1. So let's sketch in y equals -1 here. I'll grab my ruler. So there's that is along there. So what that means is essentially you're imagining that our picture is coming out of the page and we are spinning it. So imagine this is that we've got our piece of paper on the board here. We are pinning it down, maybe this is a clothesline at -1, holding it on there with a bit of blue tack or something, and then we're rotating a whole piece of paper around that clothesline. So that gives us, if you kind of imagine that sketching around, then we'll have this piece here. And it also sort of whizzes around in between values. So maybe I'll just jump out of this note for a minute just to show you what this looks like on a bit of computer software, just so we can visualize it better. So what I've got here is basically a little piece of Python code that draws this picture for us. So I don't know how well we can see this, but I've got the x-axis along here going as far as pi over 4, and the y is kind of going from 0 is here, 1 is here, and you can see the sine shape here and the cosine shape here, and the corresponding outline down the bottom. But if I drag this around, you can see how the z-axis is coming out of the screen towards me at the moment. So here's my x along here, y is up here, z is actually currently coming outwards. So if I just move these axes around, you can see the shape that has been created is actually hollow in the middle, and what I'm trying to find is the volume in between the red and the blue shell, if you like. So kind of like imagine I'm filling that space up with something. That's the volume that I'm trying to find. And so you can kind of see if I just rotate it a little bit so you can see y equals -1 again. Sometimes easier said than done. Y equals -1's along here. And imagine rotating that volume around that -1 piece of string, and that's how that shape is sketched out. Okay, so let's get the notes back. Right, so we now know what we're trying to do, and hopefully that gave you enough of a sense of what the volume is that we're trying to find. Now what we have to do is basically go ahead and do it. So you can see that there's kind of like an outer shell, which is a circle, and there's an inner shell, which is also a circle. Let's actually let's make the colors match, shall we? So the inner shell is going to be that blue one from the sine graph. The outer shell is going to be that orange one from the cosine graph. And basically, as we slide along the x-axis, those radii are going to change. So let's just call that radius r out, and we'll call this radius r in. Okay, and so the outside radius is given by, well, so remember we're rotating around y equals -1. So that outside radius starts off at 2, and by the time we've got to the end, it's dropped to about 1.7, that radius. So my radius of the outside is given by 1 plus cosine of x. Okay, it's that cosine of x value plus the additional 1 required to get from the axis down to -1. And if we look at the inside radius, that will similarly be 1 plus sine x. All right, so that kind of gives, so if we want to find this area here, of slice, if you like, this is just a chop through our surface, that's going to be pi times the outside radius squared minus pi times the inside radius squared. And so that equals pi times 1 plus cos x squared minus pi times 1 plus sine x, all squared. And finally, to work out the overall volume, we take one of these slices and then we essentially multiply it by dx to get a small piece of volume. So that's kind of taking a slice like this. Imagine that little piece delta x is being shrunk to dx as we do magic calculus on it. So that will give us the volume of a little wee slice, and then we integrate that, adding all those little slices up to give us our overall volume. So our volume is going to be the integral with respect to x from 0 to pi over 4 of this expression we just figured out. So it's going to be pi times 1 plus cosine x all squared minus pi times 1 plus sine x all squared, and that integral is with respect to x. Okay, so we've solved the problem of setting up our volume as an integral now. Now we have the separate problem, which is, can we actually integrate the flipping thing? So let's just go, see if we can make some kind of sense of it. With integrals, you always have to kind of hope and pray a little bit, but once again, this problem has come from Stuart, the textbook, and so it will have an answer, so we can feel confident that it's going to work in some way. I'll take the factor of pi out the front, integral from 0 to pi over 4, and it's going to expand out these squares. It's going to have 1 plus 2 cosine x plus cos squared x minus, and I'll expand the other square out as well, 1, now these are all going to be minus because they're all multiplied by that negative, minus 2 sine x minus sine squared x dx. Okay, or if you like, maybe we should think of it this way. Maybe it's a clearer link to the previous line. Okay, that's expanding out the squares. Now the things that we don't like integrating are cosine squared and sine squared, but maybe you've done enough of these now that you might have a clue that using trig identities will help us out here and turn them into things without squares. So it's going to be pi times the integral from 0 to pi over 4. I also see that my 1 and my -1 are going to cancel each other out. So it's going to be the integral of 2 cos x plus, so minus 2 sine x, let's put those ones first because we know how to do them, plus cos squared x minus sine squared x dx. Now this is where, if you've got some kind of table of identities, or maybe you've done a really good job of memorizing things, you might realize that that there is simply just equal to cos 2x. Okay, no real shortcut for that. It's one of those things that you may or may not know. But just hopefully what I'm suggesting you do when you come across a question like this one is just to go and look up trig identities to see if something might fit. Right, we'll just take those bits along for the ride one more time. I won't integrate, I'll just do the integral all in one hit once we're ready. Minus 2 sine x plus cosine 2x dx. And now these are all things that I know how to integrate. So that equals pi times, open a big bracket. Let's see, cosine x integrates to sine, so it'll be 2 sine x. Sine x integrates to negative cosine, so that's going to cancel that 2 off, minus off and make it plus 2 cos x. And then cosine integrates to sine, so that will be sine 2x with some kind of factor, and it will have to be 1/2, so that when we differentiate it, we'll get back to cosine 2x, which is what we want. And that's between 0 and pi over 4. All right, almost there. Now we just got to plug everything in and just be careful. So pi times, now we'll do the pi over 4 pieces first, 2 sine pi over 4 plus 2 cosine pi over 4 plus 1/2 sine of pi over 2. That's the pi over 4 bit, because twice pi over 4 is pi over 2, minus, pi is still there, don't forget that one, 2 sine 0 plus 2 cos 0 plus 1/2 sine 0. Okay, and now we just fill in the bits and pieces that we know. All right, sine pi over 4. Now is a good moment to remind you of a special triangle that helps us remember what sine of pi over 4 is. So remember that pi over 4 is 45 degrees, and if we've got a right-angled triangle with 45, then one such triangle is this one, 1 root 2, which tells us that sine, let's do it in a different color, of 45 degrees, which is also cosine of 45 degrees, is equal to 1 over root 2. I like to remember them in degrees just because radians in my brain don't agree very well, but obviously when we're doing calculus, everything needs to be in radians. But remember, pi over 4, same as 45 degrees. So let's just plug in the pieces. So that equals pi, all times 2 sine pi over 4. That's going to be 2 over root 2. Which also happens to just be root 2, we'll fix that in a minute, plus 2 cos pi over 4, that's the same thing again. Cos pi over 4 is the same as sine pi over 4, so another 2 over root 2. Half of sine pi over 2, well that's sine 90 degrees, which we know is going to be 1, so that's plus 1/2, minus pi times 2 sine 0, that's 0, 2 cos 0, that's 2. And 1/2 of sine 0 is also 0, so it's just minus 2 pi. So tidying this all up, we've got 2 over root 2 is just root 2, so it's going to be pi times 1/2 plus 2 root 2. And then it's going to be minus 2. Okay, so hopefully that is a positive thing. Let's just check. So 0.5 plus 2 times the square root of 2 minus 2 is about 1.3. So it's approximately equal to 1.328 pi units cubed. All right, and if you want, you could tidy that up slightly more. I guess we could make it negative 3 over 2. So if you want the exact answer, I could probably say something like negative 3 over 2 plus 2 root 2 all times pi. Cool, all right, that's enough for today. So we've done an area between two curves and a volume of revolution. Hopefully that will help you solve some other problems that are similar. We'll see you next time.